Alright, what's up guys? Welcome back to Matt's Math Tutorials. Today I'm going to have two videos because I forgot to do one last week because I had to go to bed early on the day that I usually film these because I had the ACT the next morning. Yeah, so basically there's going to be two videos. Alright, so this one is a AP Calculus BCU question that was on my homework. So the Maclaurin series for the function f is given by f of x equals all this stuff on its interval of convergence. Listen, no calculator test, by the way. So find the interval of convergence for this thing, justify your answer, and then show that y equals fx is the solution to the differential equation. Yeah, okay. Okay, whatever. So let's focus on this first one. Find the interval of convergence. So interval of convergence, we're looking for what x has to be so that this whole thing converges. So what I'm going to do is do the ratio test and set that the absolute value of the ratio test to be less than 1. And that will be good enough to show that it converges. So the ratio test, you do the whole thing with n plus 1 divided by the whole thing with just n. So -1 to the n plus 1 times 2x to the n plus 1 divided by n plus 1 minus 1. Okay, that should be easy to simplify at some point. Divided by, and then like I said, the whole thing except with just n instead of n plus 1. So 2x to the n divided by n minus 1. So let's rearrange this a little bit to make it easier to look at, because the whole dividing by a fraction is the same as multiplying by the reciprocal thing. We can use that to help us out here. So I'll take this. This will be the same. Oh, forgot the 1. And then 2x n plus 1 divided by, I'm just going to make that n, because n plus 1 minus 1, pretty clearly just n. And then up here, we have the reciprocal, right? So that would be n minus 1 divided by the -1 to the n times 2x to the n. All right, so now let's try to simplify this. Oh yeah, and by the way, like I said, we're setting this to be that eventually, but we're going to simplify the inside of this absolute value first, just to make it easier to look at. So if we kind of like put this over here and put this over here, right, we can see that they line up better. Might be easier to look at. But we have -1 to the n and then -1 to the n plus 1. So these are actually going to be able to divide, right? Because that's one of the exponent rules. Um, let's say like, y to the 5th divided by y to the 3rd equals y to the 5 minus 3 equals y squared. So we can do a similar thing here, right? That's just an example, a basic example. We can do the same thing here with -1. So we have -1 to the n plus 1 and then -1 to the n. So we can actually just write that as -1 to the n plus 1 minus n, which is just going to be 1, so we just have -1. Similar thing here, with that exponent division thing, that's going to become just 2x. And then we have n minus 1 over n. And we're doing the absolute value of this. We want this to be less than 1. And by the way, we're still saying this is the limit as n goes to infinity. Because remember, x is the variable we're kind of like looking for an interval for, and we know it's just going to infinity. So let's see, we have this again. Let's try to do something about this. So we have n minus 1 divided by n. Well, if we split up this into two different fractions, we would have n over n minus 1 over n, right? And so clearly, as n goes to infinity, this is going to go to 1 over infinity, which is going to be 0. So we can get rid of that, and this is going to be, of course, that's going to be 1 the entire time. So really, this whole thing is just saying multiply by 1 minus 0, or just multiply by 1. So you can kind of just get rid of that whole thing. So we're going to say absolute value of -1 2x is less than 1. And so for absolute value things, you split them up. So you have, okay, so you get rid of the absolute value, split them up. So you have -1 times 2x is less than 1. And then you have -1 times 2x is greater than negative 1. Okay, and then divide by negative 1, 2x is greater than negative 1. Remember, when you divide and multiply by negative, you have to switch the sign. And then you have x is greater than negative 1/2. And then same thing here, 2x, switch the sign, 1, and you have x is less than 1/2. So we have basically, for this first answer, that x has to be greater than negative 1/2 and less than positive 1/2. But we have to check for the endpoints because it might be less than or equal or greater than or equal. We're not sure yet. We have to check pretty much manually. So we plug in negative 1/2. We'll do that one first. And that ends up becoming negative 1, right? Negative 1/2 times 2 is negative 1. So we have negative 1 to the n times negative 1 to the n. Well, that's just going to be, that's just going to end up being 1, basically. Because it's always going to be either negative 1 times negative 1, which is just going to equal 1, or it's just going to be 1 times 1. So plugging in this for x makes this numerator always equal 1. And then you have 1 over n minus 1. And basically, that's pretty much the harmonic series. That, 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4, and that's going to end up diverging. We already know that. And I think you do that with the comparison test. So we don't want to include this, right? We don't want that. And if you plug in 1/2, just regular 1/2, you get 1 to the n, which is of course always going to be equal 1. So we're going to have negative 1 to the n times 1 over n minus 1. Now this part is the same as the other part, and we know that diverges, but this alternating, this thing that makes it alternate, right? The power of 1 is going to switch back and forth every time. That makes it so that we don't need this to converge, we just need it to go to 0. And the fact that it alternates will make it converge. So actually plugging in positive 1/2 does work. So this is our answer. If x is greater than negative 1/2 and less than or equal to positive 1/2, then this thing, f of x, will converge. And our answer is justified. I'm not going to write it because I'm using a mouse, and that sucks. But basically using ratio test. Okay, so now show that y equals fx is a solution to the differential equation x times y prime minus y equals 4x squared divided by 1 plus 2x for absolute value of x is less than r, where r is the rate of convergence from pi. So they're basically saying if this thing converges at all, right, because this is saying the absolute value being less than r means that x is somewhere in this interval that we already defined. So they're saying, and it's going to converge for anything in that interval. So they're saying if this converges, if we're somewhere where it converges, then it's going to satisfy this. So this I was kind of confused on at the beginning because I was thinking, well, how do you take a derivative of a sum, But the idea here is actually to kind of think about the sum not as just this single bit of notation, but actually as the infinite sum listed out. So I'm going to rewrite the thing over here. So it's x times y prime minus y equals, all right, definitely not going to remember that on the first try. X y prime minus y, 4x squared, 1 plus 2x equals 4x squared over 1 plus 2x. And I think that was right. Okay, so let me write out the actual thing too. So it's sum n equals 2 infinity negative 1 n, it's 2x n, and then what? N minus 1? Yeah, divided by n minus 1. Okay, so let's just start playing around and start listing out the first terms. So if n, it starts at 2, so let's say n equals 2, right? So that would be negative 1 to the 2, that's just 1, times 2x to the 2 minus n minus 2 minus 1 is 1. Okay, so basically just 2x squared, which is going to be 4x. 4x. All right, and then it's going to switch, right? Remember this is going to alternate back and forth. So when n is 3, that's going to be negative 1. That's going to be 8x to the third over 2. 8x to the third over 2. Alternate. So it's going to be plus, right? 'Cause it's going to be 4 now. So that's going to be 16 x to the 4 divided by 4 minus 3. And I think at this point it's pretty easy to see the pattern, right? Power of 2, x to whatever power of 2 divided by the thing minus 1. And so this is going to continue. Okay, so this is y, right? This is y because this is f of x, and we're saying f of x equals y. So let's start. We already know this part apparently, and this part we just multiply x. So let's think about the derivative of this. So that would be what? That would just be 4, right? Because we can do this just each one in this, separately. That would be x squared minus the x would go down a power. I think I missed something. This should be squared. So this is okay. Yeah, that's so this is squared, right? Because it's 2, 3, 4, 5, right? So that would be 8x, not 4. So 8x, and then that would be minus what? 3 times 8, 24 x squared over 2 plus what? 64 x to the third over 3, and then minus 32 times, I don't know this one, 32 times 5, 160, 160 x to the fourth over 4, and etc. So this is y. Now this is y prime, right? This is the derivative of y. So now, what if we multiply this whole thing by x, right? Well, that's just going to add 1 to each power of x. So pretty self-explanatory, right? So that would be squared. This would end up being, well, let's, I think I could do something fancy here. Probably, right? Oh, yeah. Oh, yeah. And then just go in and make this really big for a second. All right. That was pretty fancy. Okay, so x, y prime equals, so we're just going to add 1 to each power of x, right? So that becomes squared. This becomes to the third. This one, I guess I'll just erase all these. Okay. So squared, this one becomes to the third, this one comes to the fourth, this one to the fifth, right? We just added 1. So now we want this sequence here minus this one here. All right, so now if you notice, right, we're going to have 8x squared minus 4x squared. So that's just going to be 4x squared. We're going to have 24 over 2, x to the third, minus 8 over 2, x to the third, minus 16, x to the third, and then over 2. And then plus 64 minus 16, which is 48, x to the fourth over 3, 160 minus 32, that's, okay, bro. Yeah, 160 minus 32. 128 minus 128 x to the fifth over 4 dot dot dot. Okay, so there's a pattern here, right? Because to get these numbers originally, we multiplied this number by that, this number by that, this number by that, this number by that. Okay, so really, what's the relationship between 8 and 4, right? That's half, right? 1 over 2. What's the relationship between 24 and 16, right? Well, 24 and 8, that's 1 over 3. So when you subtract the 1/3, that became 16, right? So you can write this as 2/3 of this, right? This 4x squared is 1/2 of this. The 16x to the third over 2 is 2/3 of this, of this, right? Let's see if the pattern holds. So if the pattern were to hold, we would predict that we have the 64 minus 1/4 of 64, so it would be 3/4 of 64, so 48. And then again, we would predict this to be 4/5 of the 160, which is 120. So it seems like that actually works. So that means that we have a pattern here, and we can kind of like define it as a pattern, you know. So we have, one sec. Okay. So let me just go back, see exactly how I did it. Mhm. So if we were to write this, if we were to try to write this as a sum, right, we would have this, we would start with this again, infinity, right, we would have, we want it to alternate every time, right? I mean, we're basically just going from this, well, okay, let's make it alternate. So our positive, right? And then we're going to want, right, the 2x, right, because every time we're multiplying by a power of 2 and the x is increasing, right? So we start at n equals 2, so that'll be 4x squared, right? And then divided by n minus 1, right? So this should be, this is what, the same thing as we had, right? So this is y, which makes sense because y and the one we end up with, this one right here, are very much related, right? Just, times 1, times 2, times 3. I guess that's a better way to put it than what I was doing because I was relating it from x, y prime and y, but basically, you know, you're taking 3/4 of this, and then this is 1/4 of that. So you're kind of just starting from y and then multiplying by 3, starting from y multiplying by 4, starting from y multiplying by 2, right? So that's the original y. And then the changes we're making to go from 4x squared times 1, to go from 8 to 16, that's times 2, 16 to 48, that's 3, 32 to 128, that's 4. So it seems like we're multiplying by n minus 1 each time, right? For the first term, well, for the n equals 2 term multiplied by 1, for the n equals 3 terms multiplied by 2, right? So this is what our sum looks like to get us our answer here. Our, because this is x, oh, not x prime, xy prime minus y. So to get us this, we use, it looks like that sum right there is accurate. Now, of course, in this, we can cancel this out. So then we just have the sum n equals 2 infinity, and you just have -1 to the n and 2xn. So this should be the same as this, or the same as this sequence right here, which I believe it is. And so we want to get the sum that this equals, because we want to find an exact answer, because we want to show that it equals this right here. And that's a pretty exact answer, as exact as you can get without knowing x. So we want to show the actual result of this. So let's just write out the terms again. This is how I like to do sums of geometric sequences, which is what this is. I know there's like a formula for it, but I do not remember it, so I just think about it like this every time. So 4x squared minus 8x to the third plus 16x to the fourth minus 32x to the fifth, etc. So if you multiply this, so let's call this sum s. That's going to be confusing, but whatever. But if you take s and then multiply by -2x, then you get this term turns into the next term, this term turns into the next term, this term turns into the next term. So you get the whole thing just shifted with missing the first term. So if you multiply by -2x, you get the original sum just minus that first term. Um, and then you can solve for s basically, and s is going to be the sum. So -2x s equals s minus 4x squared, and then you can say 4x squared equals s plus 2x s, and then you get 4x squared equals s 1 plus 2x, and then you get s equals 4x squared divided by 1 plus 2x. And if you recall, that's exactly what they want us to find. So now we have proven that xy prime minus y equals 4x squared over 1 plus 2x when y is this function right here. So this one was pretty tricky. I didn't get this before looking at the answer key. Once I realized that they wanted us to write it as kind of that sequence, that made it a lot easier. But the hardest part was just going from, I would say, trying to find a sequence, like a sum thing like this, to match this sequence right here. Although I don't think it's too hard once you can write out y as, the actual sequence itself, and then you can find y prime and then multiply by x. It's pretty easy from there. And then just set this up and then find the actual sum of that. So I don't think this one's too out of reach, but it did involve some things that were pretty tricky. I like how my handwriting just gets bigger and bigger every time. I guess I probably could have like gone just a lot smaller, but whatever. So yeah, that'll do it for this video. Stay tuned because there should be another one also tonight. See you guys.